Hello. So what I'm going to go over is Module 13, Assessing the Fit of the Line. This is in Unit 4. So essentially what we're going to be talking about is when we add a least squares regression line to a scatter plot, then we are always looking at some sort of error because not all the um, pieces of data are going to fit on the line. So specifically what we call these errors is we call them residuals. So if you see right here, um, we're measuring the distance from the line to the point, and that's the residual. Now, if the point is below the line, it's a negative residual, and if the point is above the line, then it is a positive number. So, um, what we're going to do next is we're going to evaluate all the residuals. So if you can imagine taking that least squares regression line and flipping it to horizontal, and then putting all the residuals above and below. So basically, it's creating a graph from the residuals. So essentially, this is a way that we can actually test whether or not we should use a linear model. In our class, we're only looking at linear models, but there are other models for correlation, such as curvilinear. Curvilinear. Okay, so if you look here at A, B, and C, notice that if it has no pattern at all, if it's completely scattered like this, then the linear model can be used. This right here with this pattern, this is telling me that I have a pattern in my data that would not be best fit using a linear model. So another piece of evaluation of whether or not we're have a good model is using R squared. So R squared is taking R, which we learned about at the beginning of the unit, and squaring it. So like R, the closer that you are to 1, then the better the line describes the changes in the explanatory variable affect the value of the response variable. So this is basically saying, how much can we say that these two variables are interacting with each other? Now, does R squared usually equals 1? No, but we're looking for a higher number. So let's look at this example. So I'm not going to go to StatCrunch, but I loaded all the screenshots. If you wanted to do this by yourself in StatCrunch, then you would open this data set. So what I'm going to be comparing is the weight and the height of players. So this particular data set is from 2018. It lists all the players and a lot of different stats about the players. And usually height and weight are related, so I picked the two of those. The dependent variable is the weight, and the independent variable is the height. So that remember that when we're looking at this, what we're using mostly is X and Y. So that means this would be X and this would be Y. Okay, so here is the equation of the line. And if you look at this right here, here is R squared. And then here is R. Now, what I did is I went ahead and rounded. So here is actually the rounded line. Now, this is the residual plot. So the residual plot, remember this, in this residual plot, they don't draw the line, but remember that the line is right here, and this is all the residuals. So this is basically how far each one of the points is away from the line. So if we look at R squared, from the very top, it said R squared is 60. So that means 60% of the variability in the player's weight is explained by the least squares regression line using height as the predictor. So to the second bullet, this suggests a moderate to strong relationship. So the higher that R squared is, the stronger the relation is. That means that there's some other factors at play. So if we look at example 2, this is not example using data. It's essentially looking at the car's age and how you would predict the price. So just to maybe draw a little picture here. So we have the age of the car, and then we have the price. Once we put all that data in this example, we're saying R squared equals 64%. So 64% of the variability in the car prices can be explained by the car's age. So that means that, again, a linear model is a good fit for this example when we use R squared. So we're using two more things to evaluate, and that's the scatter plot and then also R squared. So in StatCrunch, we call this, instead of using the standard error of the regression, they call it the estimate of error standard deviation. So the estimate of error standard deviation basically says, okay, what is the standard deviation of the error? Looking at all the error, what is the standard deviation? So this is an example out of StatCrunch. So the first graph, this graph has to do with cigarettes and the deaths from lung cancer. So I'm just going to write this here. It's kind of hard to read, but this is the number of cigarettes sold per person. And then this one is the, let's see, it's the deaths from lung cancer per 1,100 people in 1990. Okay, so that means like right here, well, let's pick a point just so we can make sure we understand this graph. So this point here approximately is 29. No, that's about 20, sorry, 20 to 25. Okay, so, and this is our X coordinate, this is our Y coordinate. 20 means that 20 cigarettes are sold on average, and to 20 per person. And then the 25 has to do with how many people die of lung cancer per 100,000 people. So that's what it means. Now, if you look at the second graph, that's the residual plot. So again, you're taking the line, you're making it horizontal, and you're checking the residual plot. And this specifically is looking at the state of Wyoming. The state of Wyoming is 28.04, and the residual is negative 5.41. Notice this point is below the line. The prediction error for the state of Wyoming is larger or smaller. So if you look, basically, if you look at all those dots, do you notice there's a lot clustered towards the line? So a lot of the residuals are kind of close to the line, and they're basically, this particular point looks farther away from the line. So that means it is actually going to be larger rather than smaller. All right, if you have any questions, feel free to stop my office hours or go to the Math Success Center. Thank you for watching this video.